Well, of course, being able to take an antiderivative using the inverse trig function of the arctangent is not the only place where we might consider completing this square. Check out this guy. This looks almost like it could be one of our expressions, right? Maybe an arc sine or something like that, right? Because we've got a something minus x squared. But this isn't quite perfect yet, right? We have to figure out what's going on down here. So in this case, right, even if we have a definite integral, we're going to use a method for completing the square here as well. So let's come off to the side right here and let's complete the square. What should we do if we had the expression 3x minus x squared? All right. Well, the way I like to do it, I'm going to take my x squared term first. I'm going to make this minus x squared plus 3x, and I'm going to factor out negative 1. So I've got the negative of the quantity x squared minus 3x, and I will ask the question, what would I have to add to make this a perfect square? Well, the answer is half of 3 squared. Half of 3 squared is 9/4, right? 3 halves squared, that's 9/4. So we add that, we would make the first 3 terms a perfect square. But wherever we add, we should take away so that we are balancing the expression, right? This is just like adding 0. So now we're going to factor out that negative 9/4. So we're going to get negative x squared minus 3x plus 9/4, our perfect square, which we want, minus the negative gets distributed to this negative 9/4, and so it becomes plus 9/4 on the end. And so now we've got this beautiful new expression right here. If I reduce this, of x minus 3 halves, the perfect square, right, of which becomes x squared minus 3x plus 9/4 plus 9/4. And this equivalent expression, if I switch the two terms, is going to give me a new integral right here that can be evaluated from 0 to 3 halves of dx divided by the square root of 9/4, taking my positive term, moving in front, minus the quantity x minus 3 halves squared. And this actually looks kind of familiar, right? Because this looks almost like our antiderivative form du over the square root of a squared minus u squared. Well, it looks pretty obvious what our substitution is going to have to be right here. Let's go ahead and make our substitution u equal x minus 3 halves. All right, so du, of course, is equal to dx, so we've got that replacement right away in the numerator. The other thing we might note here, however, is that we have limits on our integration, and we can change those by evaluating u at those endpoints. This way we don't have to do a back substitution at the end. So I'd say, well, what happens at x equals 0? Well, at x equals 0, the lower endpoint, uh, we get 0 minus 3 halves, so the lower end becomes negative 3 halves when we change the variable. And when we substitute in 3 halves, which is the upper end, minus 3 halves, we get 0. So really, we're reversing the positions of these two, kind of, and we get this new integral. It's going to be evaluated from negative 3 halves to 0 of du divided by the square root of this perfect square of 3 halves. So we have 3 halves squared minus u squared. And yeah, that is our a squared minus u squared format. So we're going to be evaluating the arc sine. Remember, there was no u over a here in front of that, right? It was the arc sine of u divided by a, so it's u divided by 3 halves, and we're going to evaluate that from negative 3/2 to 0. I'm not going to do any fancy rewriting of this fraction right here, because let's take a look at what's going to happen. If I substitute in 0 for u right away, my arc sine will be of 0 over 3/2, and that's just 0, minus the arc sine of negative 3/2 divided by positive 3/2. Well, that's just negative 1. What is the arc sine of 0? Well, recall your trigonometry. This has to be equal to 0 because the only angle on the interval from negative pi over 2 to positive pi over 2 whose sine equals 0 is the angle 0, minus the only angle on the interval from negative pi over 2 to positive pi over 2 whose sine is equal to negative 1 is negative pi over 2. And that means that our definite integral, our antiderivative evaluated over the interval from negative 3/2 to 0, is going to be positive pi over 2. And that's the answer that we wanted. So we're done.